Hey everyone, welcome to the STA series, Static Timing Analysis, and this is the first video. I will do it for 12 weeks, and as I said, the first video every week, that will be public, available for everybody, but the following videos during each week, those will be for members only. Membership is very reasonable. It's $2.99 in US. And if you're in other countries, I think YouTube does its own translation. For example, if you are in India, it is going to be only 90 Indian rupees a month. Okay, so let's get started. In today's video, my focus will be to put timing analysis or timing closure of the modern chips in the context of how complex are modern chips. And what I will show you an example, a case study. I'll show you example of Intel Raptor Lake client chip, which I believe is the last of the monolithic dies. Because after that, Meteor Lake came, and now time has started for 2.5D, 3D ICs, tiles, dies, and all that. So I thought, okay, let's look into the some of the block diagram, whatever public information is available for Raptor Lake, and I can show all the students. They can look into one of the modern chip and try to see, okay, in the timing in the context of that complexity. Okay, so STA, static timing analysis. The concepts of timing is pretty simple, as I said. Okay, so all you have to do is you have to propagate delays through the entire circuit, and you propagate them through transistor, through wires, and eventually on the storage elements like flip-flops, latches, or memory inputs and all those, you check for setup and hold. Okay, very simple, right? No rocket science there. You just want to check setup and hold time. But the thing is, if you look at a modern chip, these days, okay, if I think of a chip made on 10 nanometer or 7 nanometer, okay, you're looking at a NAND gate. Okay, I'm just making some hybrid numbers. It's very hard to make the hybrid numbers because foundries are a little different, and within each foundry you have different density available. Okay, so think of a NAND gate as 0.03 square micron. Okay, and that translates into containing 1 billion transistor. You don't need that much area. If you think of 2% utilization, probably maybe 15 mm square, something like that, just rough numbers. But let's look into a chip with 1 billion transistor. Okay, as I said, modern chips will have many billions of transistors, but 1 billion transistors. Then, what is the equivalent of gates? In physical design, and when we do the layout and all that, we talk about the standard cells, gates. So, what is the gate count for that? So, gate is typically NAND, right? NAND has 4 transistors. So think of that, very rough numbers, 200 million gates. And if you have overall 200 million gates, we 10 to 20% will be roughly flops, depends on the design, but just a rough number. So that translates into 20 million flip-flops. Again, 1 billion transistor, 200 million gates, and 20 million flip-flops. So can you really do timing analysis and calculate setup and hold for all those flip-flops by doing a SPICE simulation or a dynamic simulations, right? Can you do that? That's funny. This was supposed to be a vowel, the big eyes, but the eyes kind of got removed once I converted into PDF. So sorry for that. But think of that now. Okay, considering that big chip, how will you close timing? How will you check timing? Okay, a single hold violation on your chip can kill the entire chip. Okay, and setup violations, okay, may not be catastrophic, but think of that. If you have on certain interfaces or on certain endpoints, you have setup problems, that can create a bottleneck for the performance number that you want to hit. So that can have a big impact when a chip goes in the market. So these chips, as I said, I'll give you an example of. So before I give you Raptor Lake example, just quickly. So again, looking at a higher level picture, your modern chips have billions of transistors. Okay, these are large monolithic dies. within a package, or you have 2.5D, 3Ds. Packages can be pretty big. Your dies sizes can easily be 300 mm square or more. Then they have hundreds of complex IPs. You can have soft, you can have hard IPs. There can be a very large number of clocks, going from a megahertz range to the gigahertz range. You can have a very large number of PVT corners, what we say. Your silicon can be typical, fast, slow, or anything in between. Chip might need to run on a lot of temperatures, a lot of voltages. Then you will have a different type of functional mode, different test mode. And then again, these chips, different dies come in. You have, for example, the example I'm going to give you, the Raptor Lake. Okay, that chip can go into high-end gaming PC, then can go into very high-end desktop, can go into a laptop, can go into different type of laptops, a very high-end laptop, very a medium laptop, a very lightweight laptop, right? They can have a different performance number, they can have different power numbers. So you have to design your chip with all those things in mind. And all these things create complexity. And these things make it harder for you to verify your design overall. And timing verification is one of the most important component of the verification. All right, let's look into. I thought that this would be a nice one for this a lot of students out there, because a lot of students typically they study the chips they do will be on a very older technologies, smaller chips, but it's good for you guys to study some of the modern chips. What are those are made up of? What kind of complexity it is? I picked Intel because think of this. Okay, a lot is being said about Intel, but even today, if you think with an Intel, the majority of revenue is coming from their desktop laptops. Those client projects, what they call it. If you look at some of the average numbers, each quarter, Intel revenue from the client products is about $8 billion. Yes, not million, $8 billion in one quarter. And I was searching for it. The rough kind of number of CPUs they ship in one quarter is about 50 million. So think of that. You are creating a chip which is going to be going to high volume production of millions and millions, right? And you have a target of $8 billion in one quarter. And if you are short of that, you know what happens. And the kind of pressure you have, the kind of chips you have to bring, and every new generation have to be better in terms of performance, power, form factors, and all those things than the previous one. So look at this one. I thought it'd be nice for you. By the way, all this information is public, and I have listed these websites. You can go there and search that yourself. So I took some snapshots to help the discussion over here. So Raptor Lake is a client chip. This is Gen 13. Came in 2022. Some of the versions came in 2023. The next one is Meteor Lake, which is a very important one too. I think that's where multiple tiles came, and that was 2.5D. And after that, okay, Arrow Lake, Lunar Lake, these are the guys in the market right now. So I intentionally picked this one because I think this is one of the final big monolithic die. And after that, multiple tiles came and multiple chiplets era came. All right, so the Raptor Lake was on Intel 7, which was an enhanced version of the 10 nanometer. And later on, this Meteor Lake came on Intel 4 or maybe 20A, and the future version will be on 19A. So just want to give you an idea here. If you look at this table, this is exactly what I was talking about. So you have a chip. Inside that, for example, Intel has different type of cores. You have big core, you have small core. B core is a performance core. E core is a smaller efficient core, right? But the plan is to have different SKUs. These are called SKUs, SKU. Okay, this in this configuration it will hit 15 watt. In this configuration it will hit 28 watt. And this one 45 watt, 55 watt. And actually there is one I will show you even I think above 100 watt. Okay, and you have a different number of cores you can combine and to hit different number of powers. And that will be ultra lightweight, and high performance like that. This is an interesting one to look at. So I think in that picture I don't have this version, but look at this version. And the package dimension is, look at this, 37 mm by 45 mm. It's a huge thing. And the die inside is going to be huge as well. The PDP, the power budget is 125. I also want to show you on as you go on the skew on the right side, you see another complexity there. You see there is a CPU die, and this is your peripheral controller hub, PCH, what we call it. So these are two different dies. But keep in mind, this is not your 2.5D. They are part of all the interconnection is happening within the package. There's a package tree. There's no interposer. By the way, about 2.5D, 3D ICs, I will talk about, not in the STA, but maybe some other series, and I'll give you a overview of that. So you can see that by having some of those dies done separately, probably PCH on an older technology, CPU on a later technology, you can combine, you can get the benefit of cost as well as power. Again, complexity. Okay, so this one is Raptor Lake block diagram. What kind of IOs are there? What kind of things are connected to? So look at this overall. This is your CPU die. Okay, and this is your PCH die that I was talking about. PCH is connected to your legacy IOs. All your legacy stuff is there. This is not very high performance. It need to be there because you need certain USB port. You need to have hard disk port. You need to have other things that you really need to have. But those are not your product differentiator on latest product, right? So you really need to have those ones. But this is the upper component. The CPU is where you're changing cores, where you increase the performance of the cores. And that's where, for example, you have high-speed PCI, you have DDR5 there. So all those cool things, and this is where your graphics processor, any graphics or media engines will be there too. Same picture here, just I think in this picture you have a CPU, and this is PCH. All right, I wanted to come down to this one. So you can see that now this shows a block diagram. Okay, you have on this side, this is the top part is your CPU die, and the bottom part is your PCH die. So CPU die has your cores, okay, E cores, P cores, certain number of them. And then the graphics part too, and they are connected in a kind of ring way. So very high performance, right? I don't know if I have that table, so probably you're looking into 4 or 5 gigahertz kind of interaction happening. And this is the system agent part. Okay, this is the uncore part in the CPU die. So you can see you have DDR controller, you have some USB, PCI, imaging, display, power management unit, and some of the fabric with they are connected together. This is the PCH. You can look at the Wi-Fi. You have different Ethernet, audio, SATA, USB, all that kind of legacy stuff. Now look at this chip now. This is, again, it's all this information is public. So you can take a look here from I think the wiki chip, I got this. But if you look at this, you have these big cores over here. This is the layout, okay, layout of the chip. You have a physical design done. And then here you have smaller cores. Here you have all those system agents. And here you have the graphics media stuff. Just look at this, how complex this thing is. And you are timing of this entire thing. On every node you want to calculate delay, you want to make sure no node is missed. If this missed, you really want to know why it's missed. Should it miss or not? And on all those flip-flops all over display, you want to calculate setup and hold time. And you want to be sure it better has to work, right? And this is system agent, and system agent which was on this side. Look at this. It has its own IPs. Memory configurator, memory controller, PCIs, display engine, the PCI here, and a lot of other typical IOs there. Graphics part, as you can imagine, is fully packed with a lot of logic there. And this is some of the things I put on the PCI side. On the PCI, it has all the different type of USB port, different SATA ports, and all that sort of stuff. So yeah, I think that's it. Hope you got my point. How complex are these chips, and getting out timing analysis of these chips, you have to look at so many ways. Building the timing whole methodology, checking things, making sure you check things at each hierarchy and all those. This is super complex, and that is the type of content I plan to give you and expose you to in this training. So I'll stop it here. In the next video during the week for the members, I will further look into, I'll tell you where the sign of STA happens in the physical design. I mean, how from architecture you go into micro-architecture. Again, I had an example of Dr. Lake here. And we'll look into a lot more stuff on more videos that will be coming during the week. All right, see you next time. Bye.